Good morning all, my name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is Computer Architecture. Today I am discussing about problem solving on microprograms. So what are the microprograms? What are the related to the computer architecture? So microprogrammed control is one of the two approaches. The control unit generates the signal. The control unit in a digital computer initiates sequences of microoperations. A proper series of steps must be followed to transmit any signal. Thus, address sequencing forms a determining aspect of signal transmission. So, when we are going for the operations of computer architecture, so we have to go for the micro operations. Micro operations means, suppose I have to go for the addition of two numbers. Add, mul, div. So, addition, multiplication, division, like these operations. So, for these operations, we are going for the micro programming operations. So, in the micro programmer control, the two approaches of control memory generates the signal. So, any of the micro program, we need control memory to generate the signal. Signal means from input to output. So, the control unit in a digital computer initiates a sequence of micro operations. So, when we have to generate the signals in the memory, so we need to initiate the initial sequences, but definitely we need micro operations to perform all those things. But a proper series of steps must be followed to transmit any signal. The address sequencing forms determining aspect of signal transmission. So, suppose when you have to perform input to output operations, so for this we need micro operations to perform. So, a micro operation is a elementary operation performed on the information stored in one or more registers. The result of the operation may replace the previous binary information of a register or may be transferred to another register. So, examples of micro operations are shift, count, clear, and load operations. So, when we are going for the micro operations, it is the elementary performance of the information stored on one or more registers. Suppose we have to go for the arithmetic, add AX, BX. So that means I am adding two register values. Adding means I am going for the addition. So it is a micro operation. So for this micro operation, I need registers to store the value. So definitely we need registers. So when we are going for the micro operations, definitely minimum two registers we need. Two registers we need to store the value. So AX and BX are the two registers are performing for micro operations. So here there are so many examples are there for micro operations. Shift, count, clear, and load functions are the examples of micro operations. And the result of the operation may replace the previous binary information of a register or may be transferred to another register. Suppose I am taking AX, BX. Here, suppose I am giving A equal to 5 and B equal to 4. So what is the addition value means 5 plus 4 equal to 9. So the resultant value will be stored in AX. Why? Because if I am taking add AX, BX, what is the left value? Left value means first register. So the resultant value, suppose A equal to 5 and B equal to 4, 5 plus 4, the resultant value will be stored in AX. Why? Because it is a left value. That means the first defined register. After the microprogram, what is the first register? This first register will store the resultant value. Next, if I am going for the another operation, that is A equal to 6, B equal to 3. It is one example. So 6 plus 3. But already in the previous it is 5, it is 4. But it will be restored with, when I am giving the new value, it will be restored with 5, 6 is restored with 5, 3 is replacing with 4. So here they are defining the the resultant of the operation may be replaced the previous binary value and the information of the register may be transferred to another register. Processor to be used for. So what is the processor we need in the microprogram operation? So the processor to be used for general purpose computing, specialized processor. The issue of completeness of the ISA is one of the criteria is designing the processor. That means the processor must have complete set of instructions to perform the task of the given application. Another criteria is instruction orthogonally. Instructions are orthogonal. They do not overlap to perform the same function. So when I'm going for the micro operations or micro programs, the processor definitely we need for micro operations or microprocessor. So micro programming. So the processor when I'm using for micro programs, we need general purpose computing and special processor. So why we are taking these two in the processor to use? First one, general purpose computing. So specialized processor. These processors to be issued in the completeness of ISA is one of the criteria in designing the processor. That means that processor must have complete set of instructions to task of the given application. Another criteria is instruction orthogonally or instructions orthogonally do not overlap. Overlap means overlap. Suppose my value is 4, 5 is overlapping with 4 like this, or perform the same function of the processor. Example we are taking perform micro instruction on microprocessor with 10 different instructions that perform the exact same function. So perform micro instructions. What I am taking AND gate, OR gate, these are the logic gates. So add, OR, shift, rotate, left, rotate, right, jump. So these are the micro programming operations. Perform micro instruction or microprocessor with 10 different instructions that perform the exact same function. So we have to use 10 different instructions to perform the exact same function. So we are performing micro instructions. So there are so many micro instructions are there, but here they are performing. They are asking perform micro instruction. Micro instruction means I'm taking add or anything. Suppose here I'm taking jump. So with 10 different instructions that perform the exact same function. So we have to take multiple, at least 10 we have to take. But what is a micro instruction that perform the exact same function? We have to take. So example I'm taking here jump. Let's look at the assembly code of C equal to A plus B in all three architectures. So here I'm taking jump function example. So here performing C equal to A plus B. A is one register, B is another register, and C is the resultant value. Can store. Resultant value can be stored. So stack accumulate GPR. Stack push A, push B, add pop C. Here, what is the accumulator using means load A, add B, and store C. But in the GPR function, I'm taking load R1, A, add R1, B, store R1, C. So that means load A means I'm taking the A register values can be stored in register A, and add B. That means add B means what are the A value it is adding with A, B. That means add B means we are taking add A with B. That means A plus B. A is the load function, means already the value is loaded in the register A, and B is the add B. Add B means already we know that minimum 2 registers we need to do or to perform microprogramming or micro instructions. So here I am performing microprogramming. That means two registers we need. Minimum two registers we need. So already here B is there. What is another value means already A value is loaded. So A plus B and store C. It will be stored in C register. C equal to A plus B. So push A means the A value is stored. The A register is stored with some values and B is ready. And add means add addition of two registers minimum. So add, what are the add? A already defined, B is already defined. Add A comma B. Pop C means where the resultant value will be stored in C. That is a pop C. Another is a accumulator. Load A means already the accumulator value is stored. The value of AX is stored in A and the value of BX is stored in add B and the resultant value store C. That means C equal to A plus B. So it is one method to perform. It is another method. It is another method. That means load R1 comma A. That means R1 register values are stored in A register. A equal to R1 and B equal to R2. That means R1 register values are stored in A. Suppose R1 equal to 110, 110, 11. Example. So these binary value will be stored in A. That is load R1 comma A. Next add R1 comma B. So one register is ready. What is that value? B is ready. But it is adding with what is another one? Already load is defined A. So A comma B. So already the A value is 10, 110, 11 example and B is taking 01, 01, 11, 01. So A value is ready and B is ready. So store R1 comma C. Here add function is there. Add means A plus B. So where it is storing the resultant value? Here store C already defined. So C equal to A plus B. So perform micro instruction on microprocessor with 10 different instructions that perform the exact same function. But what is the same function means? I need C equal to A plus B. Addition of two numbers and the resultant value will be stored in C. So C equal to A plus B. I need this operation in three different performances. So it is the one method stack, accumulator second method and GPR is the third method. So I am taking here example three methods for same operation. What is the assembly code of operation means? C equal to A plus B. So C equal to A plus B here performed, here also performed, here also performed. Register A, register B, and it is a register C. So register C means the resultant value of the values are storing in C equal to A plus B. Suppose here A equal to 110, 110, 11, B equal to 01, 01, 11, 01. So this value is adding with another value. The resultant value is stored in C. So C equal to A plus B. So for this C equal to A plus B, we have performed stack with accumulator and GPR. Three methods are easy. Another example, apply micro operation fields and determine micro operations for the computer with suitable examples. Apply micro operation fields and determine micro operation for the computer with suitable examples. So I am doing micro program with the micro operations. F1, F2, F3 are the micro operation fields. They determine micro operations for the computer. So I am taking three values, three functions, or here three fields. Those fields are the micro operation fields, and they determine micro operations for the computer. CD is the condition for branching. They choose the status bit condition, and BR is the branch field. It determines the type of branch. AD is the address field. It includes the address field whose length is 7 bit. So here we are taking F1, F2, F3 are the three fields or three branches, and determine the micro operations of the computer. I am going for the micro operation of this one. And CD is the condition of branching, and they choose the status bit condition. BR is the branch. field. It determines the type of branch. And AD is the address field. So CD is the condition branch, AD is the address field, and BR is the branch. So I'm defining three fields here, F1, F2, F3, and I'm performing micro operation with these fields. The micro operations are divided into three fields or 3 bits each. These 3 bits can define 7 different micro operations. In total, there are 21 operations are displayed in the table, symbols with their binary code for micro instruction fields. So we are performing micro operation with dividing into 3 fields and with 3 bits of each. These 3 bits can be defined as 7 different micro operations I am taking. These total 7 into 3, 21 operations can be displayed in the table, and these symbols with binary code for micro instructions field. So first one I am taking field 1 F1 000 001 010 011 100 101 110 111. So F1. So first I am taking 000. What is this one? Code, nothing is there. Symbol also no. Next 001. So here accumulator plus data register. Already here we are defining. DR means data register. So accumulator plus data register. We are adding S. AC plus DR means we are adding this one. So here 010, that is accumulator tends to 0. Accumulator to 0 means it is a clear operation. Clear accumulator. And clear accumulator. Clear accumulator. Next 011 AC to AC plus 1. Here accumulator is 0, empty, that is clear accumulator. Here AC plus 1, accumulator plus 1. How much you are incremented? 1 I incremented. So here it is means increment accumulator. Here INC AC. Increment accumulator. Data register. Accumulator to data register. So it is the data register is copying to this one, and AR to DR 0 to 10. So data register with a limited accessibility, and AR to PC program counter. So PC to PAR program to accumulator register, and AC plus DR accumulator plus DR data register is a write operation. Okay, accumulator plus DR equal to write operation. Here I have performed F1 field with 7. There are 3 bits of different 7 different operations. 7 different micro operations. Micro operations are performed. Next F2. Here also I am taking 7 different micro operations. Here also performing 7 different micro operations. Seven different micro operations. So here also 000 it is none. 001 accumulator plus DR, it is the sub. AC to DR or register. AC, this symbol is nothing but the, and M of AR is read operation. AC accumulator to data register, and a DR plus 1, that is a incrementing data register. Next, DR0 to 10, that is a program counter to data register. Zero zero zero, nothing. Here 001 AC2, this means XOR symbol and it is a complement symbol. Complement. Complement means, suppose, what is A complement means? A bar or equal to A bar. Equal to A bar means, suppose if I am taking equal to 0, what is A bar equal to 1? That means opposite value. 0 equal to, I will take that. Suppose here equal to 1. What is A bar equal to 0? Here also accumulator equal to 0. What is the accumulator bar? 1. So accumulator and tends to accumulator bar means I am complementing the accumulator. It is replaced with accumulator bar complement. So it is a complement. Shift left accumulator. So what is the accumulator value? I am going for the shift left. 110, 110, 11. Example. It is a accumulator value. Okay. So SHL AC. Shift left accumulator. So shift left means we are going for the shift left operation. That is the accumulator shift left. Suppose I am going for the shift right. Okay. That is a shift right means 110, 110, 11. So we are shifting right the accumulator value. So shift left accumulator, shift right accumulator, SHL, SHR. Shift right accumulator. And PC plus 1, program counter plus 1, increment PC. Increment program counter. Increment program counter. PC tends to AR and DR0 to 10 to PC. Program counter is to the data register. So how many are there now? Here 7, F2 is 7, F3 is 7, F1 is 7. So F1 equal to 7 micro operations. Here 7 different micro operations. F2 7 micro operations and F3 7 micro operations. Total how many? 21 micro operations are performed. Here 21 micro operations are displayed in a table. Symbols with a binary code of micro instruction fields also defined. Example 3. With suitable example, perform 4-bit operation mapping of instruction code to micro instruction address. So we are performing 4-bit operation. 4-bit operation example with a mapping of instruction code to micro instruction address. A special type of branch exists when a micro instruction specifies a branch to the first word in control memory where a micro program routine for an instruction is located. The status bits for this type of branch are the bits in the operation code part of the instruction. A computer with a simple instruction format is shown and the operation code of 4 bits which can specify up to 16 distinct instructions. So a special type of branch exists when a micro instruction specifies a branch to the first word in control memory and a micro program routine of an instruction located. So we are going for the micro program. The status bits of this type of branch are the bits in the micro operation code and a part of the instruction. A computer with a simple instruction format is shown and the operation code of the 4 bits which can specify up to 16 instructions. Here assume further that control memory has 128 words requiring an address of 7 bits. One simple mapping process that converts the 4-bit code to a 7 address control memory is shown. So here I am taking control memory of 128 words, that is the 2% equal to 128, that is the 7-bit address control memory is shown. Here I am taking 1011 is the opcode, operational code, and here another one is a address opcode. Here mapping of bits, here 0 means there is no mapping, 1 all zeros, 0 0. So how much is there means here same 0, 1011 0. So machine instruction, mapping of bits, micro instruction address, mapping from the instruction code to micro instruction address, mapping from instruction code to the micro instruction address. So how much is mapping? If there is, how many mappings are there? Suppose 101 some x, x011, xx11 like this. So how many related to this operation code? It will be showing how many are there. Here 0 mapping means nothing is there. So how many mappings it will be showing here. So machine instruction with opcode and address and mapping bits and a micro instruction address and a mapping from instruction code to the micro instruction address. This mapping consists of placing a 0 in the most significant bit of the address, transferring the 4 operation code bits and clearing the 2 least significant bits of the control address register. This provide us for each computer instruction a micro program routine with a capacity of 4 micro instructions. If the routine needs more than 4 micro instructions, it can use addresses of all zeros through all ones. If it is uses fewer than the micro 4 instructions, and unused memory locations would be available for other routines. So what I am taking here, the mapping consists of 0 in the most significant bit, MSB, least significant LSB, 0 1 0 1. So what is the MSB value here? 0. What will be LSB? 1. So in the most significant bit of the address, transferring the 4 operations code bits and clearing the 2 least significant bits of the control register. So what are the most significant bits? We are mapping with what one. And if the routine needs more than 4 micro instructions and it use addresses of from 1, 2, 3, 4, 5, 6, 7 bit. Here also 7 bit. If it uses fewer than 4 micro instructions, the unused memory allocations would be available for other routines. So these are the references. So microprogram operations are the 2 approaches of control memory and generates a signal. So when we have to perform the signal generation, we need a digital computer to initiate the sequences of the micro operations, and we have to transmit the signal through the address sequencing and determining aspect of signal transmission. So a micro operation is an elementary operation to perform the information stored in one or more registers. So if I am taking A, B, so A is one register, B is the another register. One or more registers. The resultant of the operation may replace the previous binary information of a register or may be transferred to another register. So examples of microprocessor: shift, count, clear, and load. Shift left, shift right, count, clear means the register is we are clearing that one. Suppose accumulator, I want to clear the accumulator. So CLR AC, that means clear accumulator, and load functions. So processor to be used for general purpose computing, specialized processor, and the issue of completeness of the ASA is one of the criteria in designing the processor. That means the processor must have complete set of instructions to perform the task of the given application. And another criteria is a orthogonality function. So here I am taking one example to perform the micro operation on microprocessor with 10 different instructions that perform the exact same function. Here I am taking some jump function for the assembly code of C equal to A plus B. So 3 architectures are there. It is architecture 1, architecture 2 and architecture 3. Example 2, apply micro-operation fields and determine micro-operations for the computer with suitable examples. Here I am taking 3 micro-operations F1, F2, F3 with determining the micro computer. So CD is the condition of branching, BR is the branch field, AD is the address field. These are included in F1, F2, F3. So the micro operations are divided into 3 fields of the 3 bit each. These 3 bits can define 7 different micro operations. In total, 21 micro operations as displayed in the table. Symbols with their binary code for micro instructions field. I am taking from 000 to 111. How many are there? 7 different micro operations are belongs to F1. Another 7 different micro operations are belongs to F2. Another 7 different micro operations belongs to F3. So I am taking for F1 plus F2 plus F3. So 21 different micro operations are performed. Here with a suitable example, perform 4-bit micro operation mapping of instruction code to micro instruction address. A special type of branch exists when a micro instruction specifies a branch to the first word in control memory where a microprogram routine for the instruction loaded. So the status of bits of type branch are the bits of the operation code and the instruction. So when the instruction format is shown, it is the 16 distinct instructions are showing, and further control memory 128 watts 2 power 7 equal to 128. So 7-bit address we need, and 4-bit micro operation code with the 7 address is shown here. So in the 7, 107 is the opcode, remaining is the address. So mapping of bit 0, 1011. How many are there? 1, 2, 3, 4, 5, 6, 7 bit. It is a mapping of instruction code to micro instruction address. And this it consists of placing of 0 in the most significant bit, MSB and LSB. So here 0, 1, 2, 3, 4, 5, 6, 7 bits. Here also 7, 1, 2, 3, 4, 5, 6, 7. So 1 all zeros to all ones. It uses the fewer than 4 micro operations, and unused memory locations would be available for the routine. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.